What's
Uday
your name?
Sunnigrohi.
Uni Uday Sanigra. No, I
Uday
didn't hear you.
Sunnigrohi.
Okay, okay.
Oh,
Uday
sorry.
Sanigra.
There is just a network problem. That's why you
Uh,
me properly.
that is fine. That is fine. It's fine. Okay. Anybody else? Okay, so we will start today's lecture, and I have posted the class notes to the classroom, and by today or tomorrow, I will also post a set of tasks, like home tasks, to be completed. Okay, and the instruction for completing the task would be very clear. Everything has to be handwritten. All diagrams should be done by pencil, or if done by pen, should be done with a scale, not just scribbled. Okay? And everything has to be labeled. All answers to be together in the sense and in order, like where answer one and then answer two and then answer three and everything. All homework for a particular homework, the homework must be submitted as a single PDF file. So you take pictures, scan them, put it to a PDF file, and post to the classroom. Put your name and roll number if you have them right there. The other very important point is try to make sure that your focus is clear when you are taking the picture, because sometimes things can get out of focus or whatever. So try to keep focus clear and the contrast high. The background should be white, the line should be dark. Sometimes they get like very small, poor contrast is difficult to read. Okay, so that are the
Okay, sir.
instructions, and I would post it. It will come with a particular deadline. Try to meet the deadline. Okay, good. So we will start
Okay, sir.
today's lecture.
Sir, this is
Yes.
my first class.
Okay, that is fine.
Sir, as I'm having some, sir, I'm migrating from another university.
Okay.
That's why, sir,
What, what,
I'm
what was your
unable to
name
attend
again?
the class.
What was your name again?
Um,
Just to clarify, you are Uday. No, right?
Yes, sir. Uday.
Yes,
Yes,
yes.
sir.
Perfectly fine. I will keep a note
This
of
is,
that. So I will post the notes on the. I have already posted. Are you part of my classroom?
yes, sir. I'm part of your classroom.
Good. So you will get the notes and go through them. If you have any questions, whatever questions, you can either post them directly to the classroom so that if I respond, everybody can look at the answers. The other one is you can ask me during class, whatever is your choice. Okay.
Okay, sir. Okay, sir.
Good. So we will start today on a different topic. So what has happened is we are jumping between physics and technology in this class. So we have done some physics. We have talked about bonding, things like that. And today we start the first classes on technology. So let me share the screen. Okay, so can you see the
Yes, sir.
syllabus? Okay, good. And I hope the slides are moving, right?
Yes, sir.
If I click, okay, good. So we will start. So today we are going directly to the fourth bullet, if you can see, concept of growth techniques, and then principles of Czochralski method, zone melting, CVD, etc., etc. So we will go through that. So these are technologies we are going to talk about, as opposed to science that we talked about. So we will start with something that we have looked at before, crystals and things, and then you have looked at the diamond or silicon lattice. And today we start with the topic called silicon manufacture. So that is the picture of the starting material. So the picture, of course, is a mound of sand that you can look at. That's the starting point. So how many of you have noticed sand? I mean, not just seen it, taken a look at it. So, if I were to ask you, describe sand in a few words, how would you describe sand? Sand is what? Particles? Yes? Use a few words.
It's a crystalline structure.
How do you know crystalline? Because, these particles made out of silica, that is fine. But do you notice that sand, the particles are very similar in size, usually,
Yes, sir.
right? That's very interesting. Why is sand very, very similar in structure? Because, as somebody said, it's these are microcrystallites. So each sand particle is a tiny crystal of quartzite. That's what it is. So quartzite is essentially the crystalline format of silica. Whatever you said, silicon dioxide is silica. Now, if it is in the crystalline form, it is called quartzite. So that is the starting point. And of course, you know that sometimes sand is white and sometimes it's yellowish, sometimes a little bit brown. Yes. Now, those are impurities because otherwise, crystallites, pure silica is transparent. It's like glass. So the starting point is the sand, and then sand, of course, is silicon dioxide. Now, in order to remove oxygen, you have to obviously react with something which has even more affinity, even more attraction for oxygen than silicon itself, and that is carbon. So you heat it in an electric arc furnace at around 1200 degrees centigrade in presence of carbon. The carbon can be from a coal or coke. It depends on the technology that is used. And you get this reaction, silicon dioxide plus carbon, silicon plus carbon monoxide. So silicon is formed. Now, silicon here is metallurgical grade with iron and aluminum being the major impurities. It is not pure yet. It's simply impure silicon. So that's the starting point. Okay. And then what we do is you take this metallurgical grade and then it's powdered and then you react with hydrochloric acid to form a mixture of silane, chlorosilane, dichlorosilane, trichlorosilane, and silicon tetrachloride. Now, do you know what is silane? Anybody knows what is methane? Methane is more well known to students. What is methane? Chemical formula?
So methane is CH4. It's an organic compound.
Right. So silane is SiH4. Okay. It's similar to methane in chemical structure, except carbon is now replaced with silicon. Silane is SiH4. Now, in an organic compound, if I were to react it with chlorine, what will happen? One of the hydrogen will get replaced with chlorine. Yes. So
Yes, sir.
SiH4 is methane, is silane. SiH3Cl is monochlorosilane. SiH2Cl2 is dichlorosilane. SiHCl3 is trichlorosilane. And SiCl4 is silicon tetrachloride. So these are the various things that you will get in which we are trying to extract trichlorosilane, which is a liquid. Okay. So next question is a very basic question from your high secondary classes. If I were to give you a mixture of water and alcohol, how do you purify? How do you separate the two?
Using fractional distillation.
What is that? What do you do? What is the process? And what is this based on? By keeping, for example, alcohol has a boiling point of say 80. So if you keep it at 85, then what will happen? Alcohol will boil out, but water will not. That is the basic principle, right? So it is a process in which you separate out liquids with different boiling points by something called fractional distillation. And then the vapor is then condensed and you get the liquid back. What is advantage of this process is it can be repeated. So if you do it twice, you take a mixture of 50-50 water and alcohol. Now, if you repeat it, if you do it once, you get about, say, 70% alcohol and 30% water. You repeat it twice on this mixture, you get more and more alcohol, it gets purer and purer. Okay. So the number of times you distill it, the purer it gets. So if you want a 99%, you just repeat it enough times until you get the purity that is necessary. Okay. So that is the process. So trichlorosilane, being a liquid, will also be purified by this fractional distillation process, and all the impurities are moved out. After trichlorosilane is purified, it is reacted with hydrogen gas to form silicon solid plus HCl. This silicon solid is the shown in the picture. Can you see the picture? Yes. Does it
Yes.
look crystalline in nature? Does it really? It looks like a lump. So it's not like a single crystal, at least, right? It has some crystalline material, as we said. So what we get out of here is something called polycrystalline silicon. Okay. So the next step of making a silicon is to crystallize silicon, to make a single crystal film out of silicon. Okay. So we will start that process now. And it is done by a process called the Czochralski process. You can see the spelling. It was invented by this person. He is a Polish person. So when you use the word, you use a little accent on the R. So it's Czochralski with a stress on the R. Now, how is it done? So all of you can take look at the picture, right? Can you see the picture,
Yes,
all
sir.
of you? So take a look at it. The first thing to notice is something called a quartz crucible. Can you see? It's like a bucket.
Yes, sir.
Yes.
Yes.
So it's like a quartz crucible. It's like a bucket. Yes. And then inside this, you have the silicon, and it says silicon melt. So it's basically molten silicon that is placed inside. How do you melt it? You place chunks of this polycrystalline silicon, and then you heat it till it melts. Okay. So once it heats up and it melts, now I'll ask you a question. How many of you have tried to freeze water inside your fridge? You take a glass of water and you put it inside fridge and you try to freeze it, right? So if I give you a
Definitely.
glass of water, can you which part will freeze first? If you put inside the fridge or the freezer?
At the top part.
Upper part.
Yes. Why? Because that is where heat can be lost very effectively, right? In order to freeze, it has to lose the latent heat. Yes. So the top part is open to the atmosphere, so it loses the heat, so it freezes. Now here, silicon melt, it's first melted, and then what you do is you slowly cool it until it is just below the melting point. So it wants to freeze. Okay, just below the melting point. It wants to freeze. But you do not want it to freeze all over in a random fashion. What you do? You add, can you see something called a seed crystal somewhere in the picture?
Yes, sir.
So that seed
No,
crystal is a pure crystal, is a single crystal, little piece that was first brought in touch with that crucible within the on the surface of the molten liquid. Okay. Now let's look at what happens next. So here, let's look at this picture. Now it doesn't have all the extra drawings, but it shows you exactly what it is. First point is polycrystalline, and then second is melt, right? It has been molded. Now, can you see the dip seed? The fourth picture.
Yes,
Okay. So
Yes, sir.
what is the seed doing? It is touching the surface. Yes. The moment it touches the surface, that becomes the coldest spot on the surface. Okay. And so, where do you think the silicon will freeze first? Where do you think the silicon will freeze first if that seed is touched on the surface, which is the coldest spot? Hmm? Where do you think it will freeze?
Top portion.
Now just think, it will freeze at the coldest spot, right? Because that's where the heat
Yes,
can
sir.
be lost. And the coldest spot is which one? The seed itself.
Yes, sir.
So it will deposit on the seed. The seed will grow because more silicon from the melt is coating it and freezing. So can you see that in the next couple of pictures? Can you see the silicon is melted and then frozen, and the frozen part is sticking to the seed, and the seed is being pulled out. Can you see that? Do you see the picture? The last one
Yes,
on
yes,
the
sir.
row?
Yes, sir.
So what has happened?
Yes, sir.
The melt is freezing in contact with the seed, and the seed is slowly being pulled up. And first there is a neck, then there's a crown, like a arrow, like a triangular head, and then the body. See that? Like a cylinder of silicon is being pulled up. What does it mean pulled up? It means the liquid is freezing and in forming a cylindrical solid body, and slowly it builds up until most of it has gone off. See that? Grow body, grow body, grow body, and then as the liquid is almost used up, say grow tail, and then you say cool and remove crystal, and then you recharge the polysilicon. So this is the entire process. It's called the crystal pulling. What does it mean pulling? You're converting the liquid into solid by first touching a seed on the top surface, allowing the liquid to freeze onto the seed. And as it freezes, obviously the volume grows, and then you draw the entire thing in form of a cylinder upwards. Okay. So any questions regarding this process? Anybody?
No, sir.
And then finally, when you do that, it looks like this. Can you see the seeds? They're like the
Yes,
little
sir. Yes,
arrow
sir.
Yes,
at the
sir.
top, and then they have grown big, 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 like a big cylinder. And then you can see these are called ingots. Now, let's go back to this picture. This shows the entire process in more detailed structure. So, you can see the liquid silicon, right? It is inside a crucible, and there's a heater that is around it, which heats up the crucible, melts it, and then did you notice something interesting? It says that the seed is hanging down from the top. Mhm. And can you see the seed is rotating? There's a circular arrow. And you see the entire crucible is also rotating in the opposite direction. So there is more uniformity. That's why you get cylindrical symmetry. That is why you have this cylindrical kind of a shape. So single crystal seed is lowered into the melt, seed is slowly pulled out. Silicon atoms from the melt bond to the seed, lattice plane by lattice plane, to form a crystal as the seed is pulled out. So you can see the neck, the shoulder, and the single crystal being formed. So this is the technology, this is the process, and this is the result. So this is something which we call crystal ingot. Now this is a single crystal, and the crystallinity, whether it's 111, 110, etc., what does it depend on? What do you think this crystal structure depends on? Which way the crystal grows? What does it depend on? Anybody? Make a guess?
Okay.
What
Can you sir, please repeat the question?
what I'm saying is, see, when we talked about crystal structures, we said There are many planes, right? There are 100 planes, 111 planes, right?
Yes, sir.
So which planes are we growing? Because the crystal must be directed towards something, right? So which plane are we growing? Which way is the crystal oriented? What should that depend on? Did you get my question?
Yes, sir.
Yes, sir.
So what should that depend on? It depends on the crystal orientation of the seed itself. If you have dipped a 111 plane of the seed, then the crystal will grow along the 111 plane, because I said the crystal is growing layer by layer, one after another. So if you have dipped the seed, which is a 111 crystal, then the ingot will also be 111. If you dip the seed, that is 100, then the ingot will also be 100, etc. Okay.
Yes.
Now, okay, let's go back. Just stop at one point here. So from an ingot, what do you get? You basically slice the ingot and you get something called a wafer. Can you see those wafers on the bottom?
Yes, sir.
So basically, these have been developed by slicing the ingot like you slice bread, so to speak. We will come to that. The starting point of silicon technology is the silicon wafer, the one that is sitting on the table. Now, doping process. So, whenever you have a belt, obviously unintentional doping will occur. The major impurities are oxygen from the air and carbon. The carbon, of course, it comes from all organic material. So, these are the impurities that you do not want. Of course, you want to dope the material, then you can intentionally dope. Dopants are introduced into the melt and incorporated into the solid. Okay, this is pretty obvious. If you add phosphorus to the melt, then phosphorus will get incorporated. So, what is a p-type and an n-type dopant for silicon? Do you know? What is a p-type dopant? Which group? Actually, it's
Aluminium.
Means pentavalent atoms are two.
no trivalent. Pentavalent is n-type.
Sorry, sir. Yes,
The
trivalent.
For in-type.
aluminium.
Yes, but actually, in reality, the only element that is used almost exclusively is boron. Okay, others are not such good dopants. How about n-type, pentavalent? So, what elements do we use?
Phosphorus.
And arsenic. So, essentially, there are actually three different n types which can be used. One is phosphorus, one is arsenic, other one is antimony. But when it comes to p type, boron is very efficient and it's very nice. So, people generally use boron. So all of these are, if you want to dope the wafer, these are intentionally added to the melt and it is uniformly distributed and it can be added and the wafer will get doped. But next point, the last line is very critical. It says impurity concentration is not the same for solid and the melt. It's not met, it's melt. I'll give you an example. So first point is, what is a solution? All of us, we have talked about solutions, right? Say sugar in water. What is exactly a solution? Is it a chemical bonded material?
No, sir.
Homogeneous mixture. So if you think in terms of atoms, so where does it sit? It sits between the atoms, right? If you have a
Yes,
crystal,
sir.
then the solvent is so. Here we are talking about not like liquids. We are talking about solid and solid. So silicon and then phosphorus inside silicon. So where does the phosphorus sit? It will sit within the cavity or between silicon atoms. Yes. Now, What is important is, now I'll ask you a question. If you take sugar and water solution and then freeze it, do you expect that the concentration of sugar in the ice and the concentration of sugar in the water to remain the same? Knowing that the gap of atoms between water molecules in the ice is much bigger than that in the liquid form. Do you think the concentration will remain the same? You understand my question, right? Actually, it's very rarely the same. Okay, most of the times the concentration, and there is a reason for that. You know what's the reason? The solubility or the amount of solution, it depends on the gap between atoms. If the gap changes, then the probability of dissolution changes. Okay, so what will happen is if you take a solution in the liquid and then you freeze it, the concentration of the impurity in the solid is almost never the same as the concentration of the impurity in the liquid itself. Okay, so that's the physical process, and we use that in a technological step that we will show now. It's called segregation. Let us assume the dopant concentration in the melt is Cl. L stands for liquid, and dopant concentration in the solid is Cs. Right? We are freezing. Right? We are freezing liquid silicon to solid silicon, and the concentration was Cl in the liquid, and the concentration was Cs in the solid. Okay. Now what will happen is K, which is a ratio of Cs by Cl, is called the segregation coefficient. Now, segregation coefficient, if it is less than 1, then the solid gets less impurity than the melt. If it is more than 1, then it gets more. Okay? Now, question. If I am freezing part of the silicon and K is less than 1, then the impurities in the melt does not go into the solid as much as it should. What happens to the additional impurity, which is not taken into the solid? Let me ask you this question again. I have silicon melted, okay?
Yes, sir.
And then Cl is a concentration of silicon, or say phosphorus within that silicon. And then you are freezing part of it. Cs is the concentration of phosphorus in that solid silicon. Okay, so far everybody is clear? Now, what I'm saying is K is less than 1, so Cs is less than Cl. The concentration of phosphorus within that solid silicon is less than the concentration that of the liquid it was made from. So, what will happen to the additional concentration phosphorus that was not taken into the solid? Where will it go? No, it will not. It will stay within the liquid. Okay. So the liquid that is left, what will happen? It will have a higher concentration of phosphorus than it had before. Yes. Let's give you a easier way to understand. Suppose the same story happened to sugar and water. You make a concentration of sugar in water and then you freeze it. Part of the water freezes, but the sugar did not go into the solid, into the ice as much as it was in the liquid. where will the sugar remain? Huh? Anybody?
So it will be inside the ice.
No. As I said, you take a glass of water and you mix sugar in it so that there is a concentration of sugar in the water. Okay, this much you got it. Everybody got it,
Yes, sir.
right? And then you put it in the fridge. Part of the water gets converted to ice. Okay.
Yes, sir.
Now, what I'm saying is concentration of sugar in that water was Cl. Concentration of sugar in the ice is Cs. But Cs is less than Cl. So now you tell me what is going to happen at this point. Sugar should have taken a certain amount of, rather, the ice should have taken certain amount of sugar, but it did not. It took less. So where will that additional sugar, which should have gone into the ice, where will it stay? Yes? Anybody? Hello? Can you hear me?
Yes, sir.
Yes,
ব্যাপারটা বোঝা যাচ্ছে না যাচ্ছে না? Are you able to understand me or not?
Yes, sir. We can understand.
So what is happening to the sugar that did not get into the ice? সেটা কোথায় যাবে? Where will it go?
it is inside the mix.
Huh? It will stay inside the water, right? So
Yes.
the water gets higher concentration of sugar.
Yes, sir.
Yep.
As you convert more and more ice from the water, the concentration of sugar in the water gets higher and higher, because every time a portion gets converted to ice, little bit of sugar is left behind. Yes? Yes or no? I want
Yes,
you
sir.
to understand this well.
Yes, sir.
Why is the concentration getting higher and higher? Because ice is not taking up as much as it should. Okay.
Yes, sir.
So the same story happens here. And so what will happen is, so if Vm is the volume of the melt, Cm is the initial concentration of solute in the melt. At a specified point in the growth process, when the crystal has volume V has been grown, Cl is a concentration of solute in the liquid, Cs is a concentration of solute in the crystal, then Cs by is given by this particular formula. Okay, where K is given by the, what is it? It's called the segregation coefficient. Okay, so this is the formula that happens because of what we just said, and so this is the. So can you tell me what happens if K is 1?
Same. Yes, sir.
Of course, but it's not 1, and then the cellular concentration of solid and the liquid will change, and see, it is given by a formula where X is a fraction of the melt that has been solidified. Okay. As I said, as the fraction increases, the concentration keeps going up and up. So this is this particular formula that has been plotted. Can you see Cs by C0? And for various Ks, see, for K is equal to 1, it's a straight line. For K is 1, it's a straight line. Yes? Horizontal straight line. So for K is equal to 0.5. Can you see that? Of impurities in the solid initially is 0.5, and then it goes up and up because in the log scale, right? And then it goes up and up and up.
Yes, sir.
Similarly, if you go to say 0.1, initially it's 0.1, but as this fraction gets solidified, it goes up, etc., etc. So what is happening is, if you look at this boule, the concentration of the dopant is not uniform across its length. That is the final takeaway message, that you cannot get uniform concentration by this process, because as you can see, as the fraction solidifies, the concentration changes unless K is 1. Okay.
Yes, sir.
Okay. So that is the problem with this Czochralski process, that uniform concentrations are not possible. Impurities from the ambient. So what are the problems with the Czochralski process? First is impurities are there, impurities from the ambient. Ambient means air. And then impurities from the crucible. The crucible was quartz. And so the quartz slowly dissolves and releases oxygen. Silicon monoxide reacts with the oxygen. Silicon reacts with oxygen to form silicon monoxide, which evaporates, but stum remains. And this silicon monoxide, which evaporates, reacts with the graphite of the susceptor, which is the heater, and produces carbon. So impurities are carbon and oxygen that stay within the silicon. So this is a problem with the Czochralski process. A, it does not have uniformity in doping, and then it has something called impurities, which are from the ambient and from the crucible, and these impurities are oxygen and carbon. So in order to get rid of that, and see, the impurities are not uniform. Also, impurities must be very low, otherwise electronic devices will not work. So we have to get rid of all of these impurities, otherwise this wafer will not be useful. So the next step is called the float zone process. So that's the next step. Okay, so can you see the picture now?
Yes, sir.
Yes, sir.
So this is the second process, which is not the Czochralski, it's called the float zone technique. So can you see the silicon bar?
Yes, sir.
So this is the solid silicon bar where there's a lot of impurity, oxygen, carbon, etc. And it is held, can you see, clamped from the top and the bottom?
Yes, sir.
And see, there's a gas inlet and outlet, so an inert atmosphere is maintained. So ambient impurities do not come in. Okay. Now, next step is something
Sir,
called yes, go ahead.
sir, which gas is used in this process?
Either argon or nitrogen. Argon is very common. Argon is a noble gas which is very inert. Also, it's a heavy gas, so it stays. It does not flow out easily. Okay.
Okay, sir.
Now the main part is, can you see the RF source somewhere?
Yes, sir.
So this RF source is basically a way to heat up by induction a very small portion of the silicon rod and heat it up to the point where it melts. That is the most important point. We will melt a small portion of the silicon rod. Now here comes the picture. Can you see the rod with the molten part?
Yes, sir.
So what we do is we melt this part using a RF coil, a small portion, and then move upwards. From the bottom, we move to the top. So in this picture, the last picture, can you see this gray area was molten, but then it has moved up. So what will happen? The top portion will melt and the bottom part will resolidify. Yes or no?
Yes, sir.
So this portion, let's change the color.
Can
I'll change the color. So yes, so this portion, it has moved up, right? So this part is now liquid, this part,
Yes.
and this part
yes, sir.
has solidified.
Yes, sir.
Okay, this part is solidified. Now, what did we say when liquid changes to solid? If the segregation coefficient is less than 1, what will happen to the impurity? Impurity in the solid will be less
Yes,
than that in
yes.
the liquid. Therefore, by simply melting and refreezing, this bottom part is made more pure, and extra impurity which did not stay in the bottom part has gone to the liquid. Yes.
Yes, sir.
So, if you do this and then you move the zone upwards, what are you doing? You are making the bottom part more impurity free, and then we are moving it to the top part. So, the top part of this rod will get progressively richer in impurity, and the bottom part will get progressively purer. Okay. So, this is the whole point. Impurities are more in the melt than in the solid, depending on the segregation coefficient. The resolidified material is purer. So, the melt carries away the impurity. Near the top end, the impurities are very high and the rest is less. So, what can we do? We'll discard the top end. The newly formed resolidified part is single crystal and much more purer. Okay. So, this is a way of processing. It's called zone melting or zone refining. And this technique is called the float zone technique. Why float zone? As you can see, the top part of the silicon is floating on a liquid. Yes. So this is the float zone technique which is used to purify a rod which has already been made. So the first part is from polycrystalline to single crystal conversion by using the Czochralski method, but it has a whole lot of impurities, both from the ambient and from the crucible. Here, can you see there are no crucibles? It is heated externally by the RF coil.
Yes, sir.
So no impurity is coming in from the crucible. Okay. So this entire process happens and then you get a much better, purer material. So float zone technique is used to purify the material. Okay. So this is what it looks like. The whole thing is like molten and everything. Now you can also dope during the float zone process by introducing gases in the chamber with phosphorus and boron. Okay. Now from the boule you can get wafers. How do you get wafers? You slice, but before slicing you grind. See, when you form this, this doesn't look perfectly cylindrical, right? This one is not perfectly cylindrical. It has some roughness, some everything. So first thing is you polish it, grind it rather, to make a perfect cylinder. This one, the first portion, and then you slice it to make wafers. Of course, after the wafer is sliced, you use a diamond saw to cut it. The surface is very rough and damaged, so use some sort of a polishing step in order to prepare the surface. It's called the chemomechanical polishing step. And then, see, this is how the chemomechanical polishing step happens. Can you see the picture on the left?
Yes, sir.
Yes, sir.
So, what has happened is there's like a pad which is rotating. It's called the chuck wafer pad. Can you see that? And then you put the wafer is stuck on that spindle. Can you see that? Okay.
Yes, sir.
Let me point out again. So this is a wafer. These are the wafers. Okay. This is
Yes, sir.
connected on this chuck, which is rotated in this fashion. And then on this pad, this is the pad on which you place something called a slurry. Slurry is nothing but diamond or other particles in a liquid, which you put on here, and then you polish it. You rotate it, and it polishes, and the surface becomes very, very smooth. And then you get wafers, which look like this. Can you see the wafers here? These wafers are here, placed in a box. So there are 1, 2, 3, 4, usually 25 wafers in a box. Okay. So that ends the process from silicon manufacture, from sand to the wafer. Okay. Any questions regarding this process?
No, sir, it's
No,
fine.
So, and then the wafers are identified by, can you see it's not perfectly circular?
Yes, sir.
So depending on that, you can identify whether it's a 111 p type, 111 n type, 100 p type, etc., etc. So looking at the wafer, you can, otherwise you will not be able to know, but the manufacturer makes these marks so that you are able to identify the wafer from the shape of it. These are industrial standards. Okay, good. I think we'll stop here. Next class will be defects. And
Okay, sir.
so far we have done crystal. So that's good. We have made good progress so far. Let's look at where the syllabus stands. Syllabus. Here. We have done principles of zone method and zone melting. Next class will be, see, the second part. Defects in solids.
Okay, sir.
Okay, good. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir.